As far as the math goes, there really isn't going to be a whole lot of new conceptual material in this chapter because even just looking at this right here, we got a double integral, we got a triple integral, and these double and triple integrals that are going to show up, at least just from a math perspective, are not different from what's shown up earlier in this chapter. So there's not really a lot of new math stuff. There aren't really any new techniques or anything. It's just this is something, or here are a couple of things where double and triple integrals would be used. So we're going to focus on finding mass and the center of mass and then moments of inertia. And the fact that you've got a double integral with the two-dimensional shape and a triple integral with the three-dimensional shape, that is kind of, it's been the way that it's been going so far in this chapter, really. But that's the biggest difference because anything that involves a two-dimensional plate, you end up with a bunch of double integrals, and anything with a three-dimensional solid, it's a bunch of triple integrals. So I guess the first thing, the one thing that might look a little bit new here is that delta. So the delta is just for density. And if you have a plate or a solid with a constant density, that is going to be an easier integration than if you have one that doesn't. So that's why the example has one that's not constant when we get there in a second. But all the other two-dimensional plate stuff is basically right here. So the first moments for a two-dimensional plate, where the only difference between these two integrals, and if I scroll for a second, and this one up here, is it's not just delta down here, right? Up here it's just you're integrating delta over dx, dy, dx. And then here we've got an x times delta, here we've got a y times delta. That's what the first moments look like. The second moments, like instead of having an x and a y, have an x squared and a y squared. But you need to get the two first moments because you use them in order to get the coordinates of the center of mass. Because for a two-dimensional plate, the center of mass is going to be somewhere in that plate, right? It's going to have an x coordinate and a y coordinate, so it's going to be a point. And so basically it's that x bar is the x coordinate and y bar is the y coordinate, and you need those two moments, those two first moments, in order to get those, right? Those are what the numerators are. So the first example is basically just going to be one of these, where it's two-dimensional plate, figure out where the center of mass is. All right, so the first example, we want to find the mass and center of mass, and I guess really just find the center of mass because you have to get the mass on the way there, of the triangular plate with those three vertices and with that density function. So we don't have a constant density. I figured it was better to have an example like this and then have the easier one where it's a constant density kind of left out rather than the other way around. So there's that triangle, and we're going to do a double integral in order to get the mass, right? So we know that the density, delta, is 1 plus 3x plus y, so there's that. And then as far as the region that we're going to integrate over, I guess it's the same degree of difficulty if you go dy dx or dx dy here. So I just did dy dx. I said, all right, well, this line, it's 2x plus y equals 2 if 1's our x-intercept and 2's our y-intercept. So if you just rearrange that so it's solved for y, that's 2 minus 2x. So then I did dy dx where I said, okay, that's the thing that's on top, and then y equals 0. The x-axis is always on the bottom, and then the x values are going from 0 to 1. So there are my limits of integration right there, right? Y goes from 0 to 2 minus 2x, and then x goes from 0 to 1. And then the integration is not bad, right? I guess, let's see. There might be points where like maybe that's a little hairy because you got to square and then multiply by a half. If you do that all in one step, it's a lot to remember. But other than that, not too bad. This actually ends up simplifying down to something pretty small. And then integrate that, evaluate it at 0 and 1. Eventually you end up with 8/3. Okay, that one doesn't seem so bad. And the other ones are kind of about the same. It's just that you do have to do 3 double integrals here. So the next one, m sub y, I guess the order doesn't really matter. I did the m sub y first because you need that one for x bar, but I mean, I guess that doesn't make much of a difference. But m sub y, the only difference is now instead of integrating delta, it's x times delta. So there's x times delta. And notice it's the same region of integration, so it's the same limits here, right? 0 to 1 for x, 0 to 2 minus 2x for y. So it's just that you're integrating a slightly different thing because you have to multiply by x. So you do that, you multiply the x through, you integrate it, and then you evaluate that 0 and 2 minus 2x. So you get this. I think this is a little bit drawn out when you multiply that all the way out. No, not as long as I thought it was. I must be thinking of a different one. But then this actually simplifies really well, right, down to 4x minus 4x cubed. And then you integrate that, evaluate that at 0 and 1, you eventually get 1. Okay, well then x bar is m sub y over m. M sub y is 1. M is just the mass, and that's 8/3. So 1 over 8/3, that's 1 times 3/8, which is just 3/8. There's the x coordinate. Now for the y coordinate. Then you have to get mx for that. So mx, it's going to be the double integral of y times delta. So there's y times delta. You distribute the y through. You integrate that one. And notice, again, same limits of integration, right? Still 0 to 2 minus 2x for y, and then 0 to 1 for x. So then you end up here when we integrate with respect to y, double evaluate that. Then I guess I did kind of an unusual maneuver simplifying this. I factored out 2 minus 2x quantity squared. So like that's what's going on down here. Like I factored this out and I said, okay, well then there's a 1/2 from the first term and 3/2 of x from the second term and a 1/3 times 2 minus 2x from the third term. And then that simplifies down to this. So this big set of parentheses right here ends up being 7/6 plus 5/6 x. And then from there, I factor a 1/6 out of there and pulled it out front. Factor a 4 out of this one, pulled that out front. And that's where the 4/6 is coming from, which would then reduce to 2/3. Then multiply a binomial and a trinomial, combine terms. This isn't so bad to integrate, right? So we integrate that, evaluate that at 0 and 1. And let's see, eventually what you end up with is 11/6. Okay, so we're almost there. So then y bar would be m sub x over m, but m sub x was 11/6. M, the mass, is 8/3. So 11/6 times 3/8 ends up being 11/16, right? Because 1, 2, if you want to cancel stuff. So, all right, well then we know x bar is 3/8, y bar is 11/16. Those are the coordinates of the center of mass. So the center of mass is just going to be the point 3/8, 11/16. So not too bad with the integration, right? It's about the same as what we've had before. But this is something where, like, this is a direct application of double integrals, is to get the center of mass of some plate or some object, which is the next thing. And this didn't apply to that last example, which is why it's coming up now instead of before that last example. But if you do have a constant density, then the center of mass is referred to as being the centroid of the plate or the three-dimensional solid. So for the three-dimensional solid example that's below, I set it up with a centroid, just so then that way we could have one. But for a three-dimensional solid, you have an extra integral that you have to do. So the three-dimensional ones are a decent amount of work because basically you end up having to do 4 triple integrals because you're going to have one for mass and then you're going to have one for each of these 3 moments. So it's a decent amount of work, right? And then if you look at the coordinates of the center of mass, you go, okay, this looks kind of familiar. You're dividing a first moment by the mass. And it's just in every case, right? The triple integral here has an x in it, and you go, well, then this is the one that you use down here. Right? This one's got a y in it. This is the one that you use to get y bar. This one's got a z. Use it to get z bar. But it is a little bit more work with the extra dimension, right? I mean, 4 triple integrals is nothing to sneeze at. All right, so here's one that we had before because I had the picture ready to go already, and the picture is at least legible. So if we wanted just to figure out what the triple integrals would have to be, so rather than doing this all the way out, I mean, the one with the 2-dimensional plate was long enough, right? I mean, it's like 2 pages all handwritten out. This one probably going to be about 3. So if we were going to get the centroid of this, and notice, and this is the thing that feels weird when it's something to do with a centroid, it's never specified what the density is. Right, like that's not here anywhere, right? It never says, delta equals whatever. So when that happens, then the assumption, if it's not stated, is that delta is 1. So that's why right here I have a 1, because I mean I think that's a reasonable thing to look at this and go, wait, where does that 1 come from? That's where the 1 comes from. It's just that if it's not stated, if it says centroid but doesn't give you the actual value, then you can assume that it's 1. And our book does that with a couple of questions, so I kind of intentionally wrote it up like that here, just so that way I could say that. But anyway, if we were going to get the mass and then the 3 first moments that we'd have to get, then you could just use the limits of integration that we used before to integrate that, right? I mean, I guess this one we already have, right? Because I think we got the volume of that thing. So we would actually already have the mass in section 15.5. But these were what the limits were. So we did it where it was z first because we said this is what's always on top. So just solve for z. It ends up being 2 minus x minus 2y, and the bottom z equals 0. And then when you go to the projection in the xy plane, so you can see it right here, you'd have x equals 2y on the bottom, and then you'd have x plus 2y equals 2 on the top. So then if you solve those for y, then you get these, right? Because then x equals 2y, same thing as y equals 1/2 x, right? And then this one, if z is 0 and then you solve for y, you end up here. And then x is going from 0 to 1, right? So those old limits of integration that we had, those you use on all of them, and it's just that for the moments, you have x to get m sub yz, and then a y for m sub xz, and then a z for m sub xy. So this one, I figure just setting it up was probably enough because this is really long. The ones that are 3-dimensional, I mean, it's 4 triple integrals, right? Of course it's long. So I figured the important thing really is just saying like, okay, this is how you set it up. Because the integration, we've kind of already done it for this example, but it's generally not too bad, but it is pretty long. The next thing is second moments, the moments of inertia. So for a 2-dimensional plate, you can figure out the moment of inertia about the x-axis or about the y-axis or about the origin. And notice for the second moments, what's the difference with the thing that you're integrating? Well, first moment had a y, second moment has a y squared. First moment had an x, second moment has an x squared. Then the one about the origin, I don't even really think of this one as being a double integral because you can split that into 2 double integrals and it ends up being I sub x plus I sub y. So every time I've seen this come up, it's always get all 3 of these. And the easiest thing to do is just get the one about the x-axis, the one about the y-axis, and then for the origin, just add them together, like it says down here. But that, I mean, that's the only computational difference. So let's see, I guess here, if R is in the first quadrant, bounded by the parabola, which you can see right there, then y equals 1, which is up there, and then we want to get I sub x, I sub y, and I sub 0. And then there's our function for density. So delta is x times y. And if you look at this thing, so I drew out the picture just to get the bounds for integrating with respect to y, I suppose. Or I guess you could do it the other way. You could integrate with respect to x first if you wanted to. It's about the same degree of difficulty. But y equals 1 is clearly the thing that's on top. And then the thing that's on the bottom is this, which is y equals x squared. So, all right, if we're going to get I sub x, the moment of inertia about the x-axis, then we're going to integrate y squared times delta. So there's y squared, there's delta, the xy. And then I did it in the order dy dx. So I've got x squared on the bottom, I've got 1 on top, and then the x values are going from 0 to 1. And then the integration here is not too bad, right? So you go, okay, yeah, that's going to be a 1/4 xy to the 4th. I pulled the 1/4 out front, and then eventually you end up with x minus x to the 9th. That's not too bad to integrate. And then that's a 4/10 in there. So you ultimately get 1/10 as the moment of inertia about the x-axis. Next is the moment of inertia about the y-axis. So about the same, except that you've got an x squared now instead of a y squared. Right? So then there's x squared times delta, the xy, right? I kept the order of integration the same. So, you end up kind of doing the same stuff. You integrate with respect to y, then evaluate at x squared and 1. And you get a similar sort of thing, just with different powers of x, I guess, and you have a 1/2 out here instead of a 1/4 this time. But then what you ultimately end up with is 1/2 times 1/8 and that's 1/16. All right. Well, then for I sub 0, you could do it the long way if you really felt like it, but I would just do this move right here where you just add I sub x and I sub y together, right? You've already got them. There's no point in redoing a bunch of work. So 1/10 plus 1/16, common denominator is going to be 80, and you end up with 13/80 for the moment of inertia with respect to the origin. Just like with the center of mass, the moments of inertia are more work with the three-dimensional solid. So they're triple integrals, and we can do it about the x-axis, about the y-axis, and about the z-axis. And there are still squares, right? Because you look at the end, y squared, z squared, x squared, right? There's squares in there. But these are the things that you end up having to integrate. So y squared plus z squared times delta, x squared plus z squared times delta, and so forth. Then a thing that I always think when I look at these is if you broke these up, could you then just recombine them faster in order to get all these three? You know, like instead of the triple integral of y squared plus z squared times delta, if you had the triple integral of y squared times delta, and then separately the triple integral of z squared times delta, and then I guess the one for x squared times delta, and then just add them together in order to get these three, you can. And I always trick myself into thinking that saves time and it saves work, and it doesn't. They're basically equivalent in terms of the length and the amount of work. But anyway, I figured that was worth mentioning because I always think that when I see these, and that's not entirely real. It's kind of a mirage. Anyhow, so another old example because I had the picture all ready to go. So if we wanted to just figure out the iterated integrals used to get the three moments of inertia, so about the x-axis, y-axis, and z-axis, for that thing right there, and assuming that it has constant density. And right, this is an old one that we've had already, so we know what's going to happen with the limits of integration, right? You could pull them out of the section 15.5 notes right at the end, but just kind of eyeballing this thing, you go, all right, the thing that's on top is z equals x, the thing that's on the bottom is z equals 0. So that's where the 0 and the x are coming from. And then the projection into the xy plane, it's a parabola that opens along the positive x-axis. So it ends up being x equals y squared, which I guess you could also see it right up there rather than doing it from the picture. But yeah, you get x equals y squared. So as far as x goes, then the thing that's farthest out is x equals 1. So then the front is x equals 1 and the back is x equals y squared. So y squared for the lower limit, 1 for the upper limit. And then the y values are going from -1 to 1 because where x equals 1 intersects x equals y squared, so like at that corner or that corner, that's what the y coordinates are, right? They're -1, +1. So there are limits of integration, and then you would just basically set them up like this, right? It's the same limits in all three. And then in order to get the moment of inertia with respect to the x-axis, you get the y squared and z squared. Y-axis, you get the x and the z. Z-axis, you get the x and the y. And there's no delta in here multiplied by y squared plus z squared or any of these others because there's the assumption of constant density that's never stated. So then you would assume that it was 1. You would assume that that constant density is 1. So that's why that's not in there.